problems like this. So take a look at what this says here. Indicate which diagram represents the volume of the gas sample in a flexible container, like a balloon, when each of the following changes takes place. So we make some change, what happens to the volume? Picture number one is the volume going down. Picture number two is the volume staying the same. Picture number three is the volume increasing. So if temperature increases at constant pressure, what happens to the volume?
It will be small.
Temperature increases?
No, it will be bigger.
Right. So if you heat it up, it will expand and get bigger. So number three would be the answer to that. What if temperature decreases? Temperature goes down. Yeah, smaller. So number one. What about if atmospheric pressure increases but temperature stays the same?
The pressure increases, what we have like a balloon, it will be smaller.
Right.
The pressure.
Right. And then if the pressure decreases?
The pressure decreases, it will be bigger.
Right. So it's the opposite. And then what if you double the atmospheric pressure and double the Kelvin temperature? Kind of a tricky one. So think about what happens here. You double the pressure and you double the temperature.
Still the same. It will not change.
Yeah. Why?
Because we double both of them. So
yeah.
If we double only one, yours will be different. Like,
yeah, because those have opposite effects. Right? So you double the pressure, the volume goes down. If you double the temperature, the volume goes up. So if it goes down by double and then up by double, it's really staying the same. So that one is number two, the same. So that's the kind of ideas that we're going to be using these gas laws for. All right, so I said at the end last time that one thing I wanted to look at with gases is how do we explain how this is happening? The laws are the laws, and then we have to think about what is actually causing those laws. Like gravity. We know the law of gravity, things attract each other. But what is the reason for that? Right now? What is the reason for gravity? Where does gravity come from? Why do things attract each other in that way? Not related to this, but I don't know if anybody knows that. It's because of the idea of space-time, the fabric of time, and that gravity kind of pulls things toward each other as depressions in space-time. I don't know. You can read some physics if you want to, but it's all kind of crazy. But anyway, that's the idea of a theory behind a law. So we're going to look at the same thing for gases. And the one behind the gases is called the kinetic molecular theory of gases. Kinetic meaning motion. So the assumptions of the theory are basically that gas molecules are moving very fast, and there's a few other things that are causing what we see. So here are the kind of the parts of the kinetic molecular theory. First, gases consist of small particles that move randomly at high speed. So gases are tiny particles that are always moving and not moving in the same direction, moving in random directions all the time. So always moving really fast, and in random directions, any directions. The second assumption is that attractive forces between gas molecules are insignificant. They don't matter. So gas, we talked about intermolecular forces in liquids and in solids, and these forces that kind of hold molecules together. And we're saying that in gases, those forces don't matter. Because the molecules are going so fast and they're so far apart from each other, we don't have to care about the attractive forces. So there are no attractive forces. Now that's not entirely true, but it's a reasonable assumption that will explain most of what we see. In certain circumstances, that breaks down a little bit, but for our purposes, that works out nicely. Third, the actual volume occupied by the gas molecules is tiny, very small, compared to the volume the gas occupies. So that means that if we have 500 milliliters of a gas in this container, most of this is just empty space between gas molecules. The actual volume that the molecules take up is tiny. It's insignificant. It doesn't matter. Most of the volume of a gas is just empty space. So what that means is we don't have to think about the volume of the particles themselves, which is why the volume of a gas can change with something like pressure. You can't change the volume of liquid with pressure. You can't pressurize liquid and make it take up less space. And that's because there's not really space in between the molecules. They're very close together. But gas molecules are so far apart that when you compress them, all you're doing is changing the amount of space in between them. And so that will help us to kind of explain what these molecules are doing and help us to understand that we don't need to care about the size of the actual molecules. It doesn't matter. All right, so those are the three kind of assumptions behind this thing. And then the last two kind of are the things that lead to the effects that we've just seen. So we're going to spend a little more time with these. This one says that gas particles are in constant motion moving rapidly in straight paths. That doesn't seem very important, but here's the effect of that. Gas particles are always moving and moving fast. We kind of already talked about that. But the really important part of this is the straight paths. Gas molecules don't have little rudders that can change direction. There's no steering wheel on a gas molecule. So when they're moving in a straight line. And when they hit something, they bounce off that thing and go in a different straight line. But they're always going in straight lines. What that means is that every gas molecule will eventually hit the walls of the container. Because if you're traveling in a straight line and you don't turn, eventually you will hit the wall. Right? If we all got up now and we just started running in a straight line in any random direction, we'd all hit the wall eventually. So that's important because then we define those collisions with the walls as pressure. So where does pressure come from? Pressure comes from gas molecules hitting the walls. So anything that causes molecules to hit the wall more will lead to an increased pressure. And anything that causes them to hit the wall less will lead to a decreased pressure. So we can think about something like Boyle's law. Boyle's law says that pressure and volume are inversely related. If you decrease the volume, you increase the pressure. Let's think about how that works in terms of what's happening with the actual molecules. So let's imagine we are all gas molecules, and we are running around the room in straight paths, and we're all hitting the wall a certain amount of time. Every time we hit the wall, that creates pressure. So if the room gets smaller, but we're still all running the same speed and there's still just as many of us, we're going to hit the wall more, right? Right? So that means there's an increased pressure. Those increased collisions with the walls are that increased pressure that we're talking about. So that's the way that we can explain what's happening with these laws. And then the final piece of this the average kinetic energy of gas particles is proportional to the Kelvin temperature. So let's think about what that means. I don't know if anybody's ever taken physics here. Kinetic energy, the energy of motion, the equation for that is 1/2 mv squared. You don't really need to know that equation for this class, but you should know that the m stands for mass and the v stands for velocity, speed, how fast things are going. So that means that the temperature is a measure. Remember, temperature is not directly a measure of energy, but the temperature is proportional to the energy, to the kinetic energy of the gas molecules. So if we have a sample of gas and we heat it up, what we're doing is we're making the gas molecules go faster. We're making them go faster. Similarly, if we have two types of gases, let's say helium and argon, so helium and then argon going down, and those two samples of gases are at the same temperature, the argon is moving slower than the helium because it's heavier. And so since they're at the same temperature, they have the same kinetic energy. So that means that if they have different masses, one has to be going faster than the other to have the same kinetic energy. So let's think about how this fits with the gas laws that we've just talked about. First, if we look at something like the relationship between pressure and temperature, increasing temperature does what to pressure? Increases the pressure. It's a direct relationship. So we can explain that using these ideas by saying an increase in temperature means that the gas particles, what is changing in the gas particles if we increase the temperature? Right, they're going faster. And so if they're going faster, what does that do to the collisions with the walls? Yeah, so it increases those collisions, right? if we use us as an example, just because it's kind of funny to think about everyone running around and running into each other. If we all stood up and we cleared out the tables and we started running around, we'd hit the walls a certain amount. And then if we all started running a lot faster, we would start hitting the walls more. And that's pressure. So that's the increase in pressure. Okay. We can think about this with any of those relationships, like the last one, Avogadro's law that we talked about. Increase in moles of gas leads to an increase in volume. So you put in more gas particles, the volume increases. Well, that makes sense because if there are more gas particles around, but everything's going the same speed, there would be more collisions with the walls. But since pressure is held constant here, if we want to keep pressure the same, the room has to get bigger. Otherwise, the collisions are going to be more. So if we want to keep the same number of collisions, we got to have a bigger room for more people. And that's the increase in volume. So we can think about these effects kind of back and forth, why these gas laws are the way they are. It's also a nice way to help you remember what's happening in the gas laws. If you can think of, this is really the best way to do it. If you can think about this and use that to figure out the gas laws, then you know you really understand it, because you can use these kinds of principles to figure out what's going to happen between pressure and volume instead of just remembering what happens between pressure and volume. So let's look at another example like we just did from the book, but this time increase or this time add that reasoning behind it from the kinetic molecular theory. So the question asks, indicate if the pressure increases, decreases, or stays the same in these changes. But I want to also add why. What is happening to the particles themselves that is causing that change? So what's happening in that first example in A?
We make the small.
Right. So the volume is going down. Okay. So what does that do to the pressure? Increase the pressure. Why?
Because the small plates
Mm-hmm.
and hitting the walls will be faster.
Right. Well, more collisions. It will hit more times. But yes, exactly. So the smaller container, the smaller volume, means that you'll have an increase in collisions with the gas molecules in the walls. And that is higher pressure. All right. What's happening in the second example, B? What's changing there?
Increasing the gas.
Yeah. So you're increasing the moles of gas, the number of gas particles. So what does that do to the pressure? Increase the pressure. For the same reason, right? More gas molecules will hit the walls more, so you'll have more collisions with the walls. So that's an increase in pressure. Right, good. And what about in the third example? What's happening there? Yeah, there's some burner there, so you're increasing the temperature there while keeping the volume constant. So what happens to the pressure? Yeah, it goes up. Pressure is going to increase with increase in temperature. Now, why?
Because making
Yeah.
faster.
Right. So the increase in temperature is accelerating the gas molecules, making them move faster. If they move faster, there's more collisions with the walls, and that's an increase in pressure. So that's what we want to know about gases. Yeah.
The compressor for tire,
Mm.
you add its air to the tire.
Yeah.
It's work to heat it or to decrease the space.
Neither. You're adding gas. So you're putting more gas in there, more gas molecules in there, and that increases the pressure. So it's like B. The compressor takes the air, puts it at a high pressure, and then puts it into the tire.
And when you drive like a faster, the pressure on the tire will change.
Yeah.
Even it will be hot.
Right.
It will change more. Like if if you drive like 80 miles an hour, like the tire will have two number of degrees. But if you drive like a 200, like a 100, it will be 3 times.
Is that true?
3 degrees because the tire is already hot.
Yeah.
And the speed is faster.
Is the speed making it get hotter? Is that why? Okay. Yeah. Because of the friction.
It's not about the speed for the tire. Yeah.
Okay.
It's not only the speed for the tire, because I think 2 things in one thing, like heating and also the speed for the car.
Yeah, I think that makes sense. Yeah. All right. So you think you can do that? This is as far as we'll go in these types of questions. So when you see, if you look in the back of the book there, all these things about all these questions about changing the V and N and all these numbers and things, we're not going to do that. So don't do that stuff. We'll just stop there. There is one other thing that I want to show you about gases. And that is something called partial pressures. And this deals with a mixture of gases. So in a gas mixture, the total pressure is the sum of the pressures exerted by each gas. So this is the same as what we've just been talking about. If all 6 of us are in this room and we're the gas molecules and we're running around, and we're all 6 different kind of gases, the total pressure is going to be the collisions from me and the collisions from you and the collisions from you and the collisions from you. But each one of us has really our own pressure. That's the collisions that we are making. And so we can say that the total pressure in the container is all of the individual gas pressures added together. And this is called Daltons Law. Let's look at a picture from the book, I think, that will make it a little more obvious. Rather than trying to draw it myself. All right, so take a look at this picture of these gas tanks. So I have one gas tank on the left here that's helium, and the pressure of helium in that gas tank is 2 atmospheres. So the helium atoms are bouncing around, they're making 2 atmospheres of pressure. I've got another gas tank that has 4 atmospheres of argon in it. All right? If I mixed those 2 gases together in the same volume, the total pressure would be 6 atmospheres, because it would be the sum of the helium pressure and the argon pressure. So we would say the helium pressure is a partial pressure. So that would be like the partial pressure of argon that I've highlighted here. And then those things added up is the total pressure. So the total pressure can be broken down into partial pressures of each gas. that's important because of how we deal with gases and how we measure gases. It's not always useful to, like we said last time, to weigh a gas or to think about the masses of a gas. So a lot of times when we deal with mixtures, instead of talking about concentrations and this kind of stuff, which we will also do in the next chapter, we talk about partial pressures and total pressures. Like with air, if we wanted to talk about the makeup of air, how much of air is nitrogen, how much is oxygen, how much is carbon dioxide, all this stuff, we might describe that in terms of partial pressure and say it's this much of oxygen, this much. So I think those numbers are in the book. Let's take a look at them. Well, here's an example. It's not regular air, but this is for breathing. So here are partial pressures of gases during breathing. Assuming you're breathing at atmospheric pressure, the total pressure of the air is going to be 760 millimeters of mercury, 760 torr is another way to say that. And first is the inspired air, which is the air that's coming into your mouth. Then you have the alveolar air, which is the air that's down in the very bottom of your lungs. And then the expired air, the air that's actually coming out. So you can see how the proportion of gases changes by the partial pressures of each kind of gas in each type of air. So the air that comes in is 160 millimeters of mercury partial pressure. That's like the regular air. Then when it's down in your lungs, it's goes down to 100. And then the air that actually comes out after that, that exchange is then 116. So that represents the difference in oxygen that's happens when you're breathing. And what makes up for that difference? Well, primarily the waste products, carbon dioxide and water, that are coming out after your body uses the oxygen. And so partial pressure is one way to monitor that. If you're dealing with something like scuba diving, like going underwater, you might have a tank that has a bunch of different kinds of gases in it, depending on how deep you're going, and that would be measured by partial pressures. So you'd have this much partial pressure of nitrogen, oxygen, there's some helium in there sometimes, that kind of stuff. So that's another way to measure gases. All right, so that's it for talking about gases. Just be aware of these trends and these other ideas. Are there any questions or things you want to look at more before we go on? No? Yeah. All right. Well, the next exam will be 2 weeks from Wednesday. So next Wednesday is a lab. Then we have spring break, and then the week after that is the second exam. So I want to look a little bit about chapter 7 or chapter 8. The next, whatever the next chapter is, I think it's 8.
Guess is 8, chapter 8.
Oh, gases is 8, right? Yeah. So 9.
Chemical reactions.
So solutions, chapter 9 is where we're going next. I want to look at this a little bit so we have some time to kind of process it and practice it before the exam. So let's do that now, unless there's something else you'd rather talk about more of.
I was just a little confused on the diagram with the 3 sets of the balls with the molecules, because the third one looks like they were both the same.
Yes.
Is it because the flame?
Because the flame
makes a difference?
Is making it hotter.
So if that flame was not there, then you would say that.
Then you would say nothing's happening. Yeah. Yeah. Right. Because none of these diagrams are showing pressure, which is why it's asking about pressure. So we could maybe assume that the pressure was increasing for this, but we wouldn't have any way of knowing that. I think it's the flame that we're looking at there, the picture of the burner. Yeah. Okay, let's look at a new sheet here. All right, solutions. Now this is something you kind of know about already because we've been using them in lab. How would you define solutions? What is a solution? Yes, true. What about the physical thing? Like if I said in lab, go get a solution of sodium chloride, what is that?
It's
Liquid,
solvent.
solvent, these are all words that are important, solute, solvent. So what is a solution besides the answer? What? How, okay, so it's, yeah, we can think about what's in there. We can think about what it is. It's really a type of something we've already talked about. It's a type of a mixture.
It's composition of two solids, yeah.
Yeah, the composition of two things. So there's a couple ways to describe it. It's really, a solution is really just a special type of homogeneous mixture. The thing that's special about it is the level at which the different parts are related. So homogeneous mixtures can have all kinds of different scales. But in a solution, we look all the way down to the molecular level to see how the two things interact, two or more things interact. But a solution is really just an interaction of two things. A solute and a solvent. What's the difference between a solute and a solvent?
Solvent, it's like molecules and solute. No, solute is like molecules and solvent is water, something like a liquid.
Mm-hmm. So usually when we think of a solution, we think of a solid solute and a liquid solvent. So a sodium chloride solution would be sodium chloride dissolved in water. And sodium chloride is the solute, and water is the solvent. But actually, that's too specific of a definition, because there are lots of different kinds of solutions. And I think this table in the book does a nice job of showing that. So I want to pull in this table. So you can see here that there are all kinds of solutions. Usually the one that we're most familiar with is this one. A solid dissolved in a liquid. But there's actually all kinds of different solutions. You can have a liquid dissolved in a liquid, like when we use acid solutions in lab, like 6M HCl or 5% HCl. That's a gas dissolved in a liquid. Yeah, something like vinegar or alcohol that you like buy in the store would be a liquid dissolved in a liquid. You can also have non-liquid solvents. You can have a solid dissolved in a solid. That's called a solid solution. So things like alloys, brass and steel, where you have different metals mixed together and melted together. That's a type of a solution as well. You can have gas solutions. Air is a solution, where the solvent is a gas, nitrogen, but the solute is also a gas. So given all these different types of solutions, how could you define what the solute and what the solvent is? What is it that makes something a solvent versus a solute in this type of a mixture? It's actually a pretty simple definition. Think about air, for instance, the top one there. So air, we're saying, is a solution. And according to the table, nitrogen is the solvent and oxygen is the solute. Other gases in the air, like carbon dioxide, water, would also be solutes. So what is it about nitrogen that makes it the solvent? About what? Nope, not in this case. Simpler than that. But yeah, that's it. It's just the amount. So whatever there's the most of is called the solvent. And whatever there's less of is called the solute. That's usually how we define that. So in air, we just name it, we name nitrogen as the solvent because there's more of it. Same with these others. Now, that's not always going to be the case, but it's a good generalization. In the liquid solutions, the liquid is, in the liquid solutions, when there's a solid or a gas dissolved in the liquid is always the solvent. That's usually how it is. And then another important note, probably, when there's water in a solution, water is usually the solvent. So for example, water and ethanol have infinite solubility, meaning that you can mix as much ethanol you want in with water and it will continue to dissolve. But at some point there will be more ethanol than water. So shouldn't that really be a water solution in ethanol? Probably, but we keep calling water the solvent. So if you ever looked, and we'll look at this a little bit also, but if you ever look at alcohol percentages on things like wine and liquor and those kinds of things, they'll say 10% alcohol by volume or 20% alcohol by volume. Well, once it gets to 50%, that's really, now there's more ethanol than water in there. But just to keep everything the same, water remains the solvent. So, so that's just the definition, and that's really all there is to it. We can't be more, we have to stay pretty general because there's all these different types of solutions. So let's look at what's happening on a molecular level in a solution, or when a solution is made. Let's look at sodium chloride and water. This is a weird kind of equation because it's not really balanced, but we could say sodium chloride solid plus water gives us aqueous sodium chloride, meaning that the sodium chloride is now dissolved. It's not a chemical reaction, so that's why it's not balanced or anything. It's just describing a process, a physical process. And let's look at what's happening on the atomic scale. So sodium chloride looks like a bunch of spheres packed together. Sodium and chloride alternating packed together. So something like this. Chloride ions are bigger than sodium ions, so that's why I drew them that way. Something like that. So the sodiums and chlorides are all packed together in solid sodium chloride. So here's what solid sodium chloride looks like. Of course, that's going on in all dimensions. Alternating sodium and chloride ions. So what does water look like at the molecular scale? Well, water is also a network. Remember we talked about these hydrogen bonds in water? So it's a network of water molecules all stuck together with these hydrogen bonds. So let's draw that. We've got we'll just draw a couple here, but we have these polar interactions between the partial negative oxygens and the partial positive hydrogens. And then that goes on for all through the entire water sample. And there's our liquid water. So you have these two pure substances, assuming they're pure, with their own interactions on their own there. And then when they get together, we have what we call a solution. So what's going to happen here is the sodium and chloride ions are going to split apart from each other and instead be surrounded by water molecules. Let's have a little room to draw this. So a sodium ion is going to have a positive charge. So it's going to be surrounded by a sphere of water molecules where the negative parts of the water are oriented toward that ion. Okay, and I'm drawing it in a circle because it's on paper, but really it would be a sphere. It would be all around that ion would be a bunch of water molecules. Then these water molecules would be connected to each other and also to other molecules just as before. And somewhere far away would be a chloride ion. And since the chloride ion is negatively charged, it will be surrounded by the other side of the water molecules. So the hydrogens will be more oriented toward the chlorine. Something like that. So that partial positive from the hydrogens is around the chlorides. The partial negative from the oxygens is surrounding the sodium ions. And those are then held in solution through those interactions. So we can. So this is what's happening then in that solution. And this is what we call our aqueous sodium chloride. So that means that those interactions between the molecules and the ions have to be strong enough to allow that sodium chloride network to break up, because otherwise it would just stay together. When we talk about solubility, that is how well does something dissolve in something else, this is what we're talking about. How well can the solvent arrange itself around a given solute in order to separate it from its friends, from the things that it's like. Oops. So then the other piece of this is what we call solubility. And we're going to look at solubility in from two different ways. Today we're going to look at it, how it relates to polarity, and then next time we're going to talk about it in terms of just amount and numbers. But something like pentane, let's say, which is this big molecule of carbon and hydrogen. This molecule is nonpolar, right? Carbon and hydrogen have no significant difference in electronegativity, well, just a little difference. And so we call this a nonpolar molecule. Which means that a sample of pentane, a little beaker full of pentane, all the pentane molecules, it is a liquid, the pentane molecules are going to be stuck to each other with dispersion forces. So we might draw that, and they kind of have a zigzag shape like this. So something like that. So here's pentane molecules. Stuck together with dispersion forces. So that means that pentane is not going to be able to do the same thing that sodium chloride did. That water can't break up and surround pentane because pentane is not polar. So if we had a sample of pentane and water, I'm just going to copy my picture of water here again. So water has these polar hydrogen bonding forces. Pentane has these non-polar dispersion forces, which means that they can't really mix together. One can't dissolve in the other because they can't break apart each other's forces. They have different kinds of forces. The water molecules are stuck together with hydrogen bonds. And that means that those two are not going to mix. No solution here. They are not soluble in each other because they'd rather stick with each other with their own intermolecular forces. And that's why we observe things like oil and water don't mix. Because the oil has its dispersion forces, the water has its hydrogen bonds, and those forces aren't going to break each other apart. They're going to stay with the ones that they like. So we can't really make solutions out of these types of things. But there is one way you can trick it. We can use something that is part polar and part nonpolar as an intermediary, as a way to make them relate to each other. So this is a molecule that we would call a soap. And in this kind of a molecule, you have a carbon with a couple oxygens with a negative charge, so it's actually an ion on the end. But then the other end is a really long carbon-hydrogen chain. So these are all carbon atoms with hydrogens coming off of it, just like pentane. And that means that this side here is really polar because of its negative charge and its oxygens. An oxygen-carbon bond is really polar, and that's where that charge is. And then this part here, the rest of it, is nonpolar. So that polar end is going to want to interact with other polar molecules like water. The nonpolar end wants to interact with nonpolar dispersion force stuff like pentane. So what happens in solution is these molecules form these little balls. Where the big, long, nonpolar tails point toward the middle, and the polar oxygen parts go to the outside. And again, it's not a circle, it's a sphere. It's like a ball of all these things with their nonpolar tails pointing toward the inside. And that means that the inside of this ball is a nonpolar environment, dispersion force environment. The outside of the ball is a polar hydrogen bonding environment. So the outside of the ball will happily interact with water molecules. And the inside of the ball will happily interact with nonpolar molecules. So if you wanted to, say, dissolve pentane or something nonpolar, you could find a way to get it in the middle of this thing called a micelle. You could then dissolve it in water. And this is exactly how soaps work. The grease, the dirt, the oils on our hands are nonpolar. They stick together with dispersion forces. And so water doesn't really wash them off very well on its own because they don't dissolve in water. But when we use soap and we scrub really hard with the soap, we're breaking all those things up into little particles and getting them stuck in the middle of these spheres. And then the spheres themselves can get dissolved in the water and get washed away. So there's this saying, like dissolves like. Have you ever heard that? I've heard anything like that before. But I think they talk about it in the book. Like dissolves like, meaning polar things dissolve, polar solvents dissolve polar solutes, and nonpolar solvents dissolve nonpolar solutes. That's true to an extent, but there's other molecules that can actually bridge that can change that a little bit. So it's better to think about it in terms of what are the forces. The same types of forces are always going to go together. Nonpolar dispersion forces go together, and then polar ion hydrogen bonding type forces go together. And then you need some special kinds of molecules like these to make those go together. Otherwise, they're always going to stay separate. So that's the idea of polarity and water. Here's some nicer pictures of kind of how those molecules might interact with hydrogen bonding like that. And then, yeah, we won't really get into that. So we don't have a lot of time. We'll get into this stuff next time.
I have a question.
Yeah.
You just about the floating the top, like the water on the top and the oils on the down.
Yeah.
So it will be max same thing, like because it's not coming in the middle or something like that. Yeah.
Right. So like this.
Yes.
Yeah. So in A, we have nonpolar dichloromethane and polar water. So nonpolar on the bottom, polar on the top. They don't mix because this dichloromethane CH2Cl2 is nonpolar and the water is with the polar forces. So then if you put in iodine, I2, which is nonpolar, that dissolves down here but not up here. And if you put in nickel nitrate, which is green, which is polar, that dissolves in the water but not in the dichloromethane. So if we put some kind of a soap in there, we could get it all to stay together instead of making the layers. And we're going to do this type of experiment in lab on Wednesday. We're going to try to dissolve things in different polar versus nonpolar solvents and see which thing dissolves in which. I'll try to make some guesses about that. All right, so we didn't do a lot of problem-based stuff today, but we got about 15 minutes. Do you want to go back and look at some equation problems or something like that? Practice that a little bit? Okay. I pulled up this really big document of random practice questions. Let's see if we can figure out some of these. So complete the equation. Now you're told here this is a single replacement. So what do you think the products are going to be? Yep. Now, how did you know, because this comes up in these single replacement questions a lot, how did you know that the H2 would go with the O and not with the Cu? Why wouldn't it be H, what?
The chart.
What chart?
Like, yeah,
Yeah.
Cu will be positive.
Right.
And O will be minus.
Right.
And those things will be.
Yeah. Yeah. So that's the right answer. That you want to look at what is more likely to make a positive or a negative ion, and then make sure the positive and negative stick together. The other answer is you think about what you've seen before and what you know. So you know H2O is a common thing, so it's likely that's going to be one of the answers. So that's another way to think about it. I wonder if there's another one here that has a similar. Another one of those single replacements. Anyway, sometimes it's a little less obvious, but you can usually use that same logic and still figure it out. Like this one. Okay, here's another one. H2O and F2. What are those products going to be? Well, that's a possibility. So let's look at the different possibilities here. It's single replacement, right? Which means that we have to take one of the H2O atoms, either the H or the O, and we have to put it with the F, and then the other one stays alone. So we also have to think about how these things would make a compound. The best way, even though these are covalent compounds, I think it's best to think of it as though it were ions, because H kind of goes in that column with some of the other ions. So if H goes with F, that makes HF, right? Because F is -1 and H is +1. Now this is, again, not ionic, but that's okay. And that means the leftover thing is going to be O. But whenever oxygen is by itself, it should be O2. Now the other option would be the H stays by itself and becomes H2, and the O and the F go together. Now, do we know how O and F go together? How many O's, how many F's? Well, you're all pretty sure about this. We don't know. There's no really, look at O and F, they're right next to each other. So it's true, there are compounds of O and F, but it's not clear how that would work. It could be OF, it could be OF2, it could be O2F, it could be OF4. there could be various ways that we arrange those atoms. So that tells us that this is probably not as good of a choice as this other one where we know what those compounds will be. And this is not balanced, so yeah.
I thought about OF, it will be like a minus minus, the charge it will be minus minus, so we cannot like make them.
Right, that's another way to think about it. Yep. So if we balance this, we would need to have like this, and then four of these, and then two of these. Yep. All right. Let's look at one that has some other calculations in it too. It's kind of hard to read this one, but it says, in the reaction of silver nitrate with sodium chloride, how many grams of silver chloride will be produced from 100 grams of silver nitrate when it is mixed with an excess of sodium chloride? So I'm going to zoom in on this so we can see the reaction better. And it says it's at 100 grams, right? It said, if you have 100 grams of this, how much of that will you make? Yeah. So give it a try.
We have to balance this or not?
Well, that's always the first step. So look at even if you're given an equation, make sure you look at it and see if it needs to be balanced. So what do you think? Is this balanced, or do we need to balance it? Yeah, this one is balanced as it is. It works.
So we need for AG and 3, 100 grams.
Right. All right, we're almost out of time, so I'm gonna make sure to write this down here. What's the molar mass of silver nitrate? Anybody get that?
169.91.
Is that right? 169.91? 170?
Yeah.
Okay. Yeah, same thing. What'd you get?
With 84 and 4.
Let's see. Oh, okay. I haven't gotten there yet. Yeah. So then this is 1-to-1. And then-
3.
35.5 and 107.9. Okay, yeah, so close enough. 100 divided by 170 times 143 is about 84. And since we rounded a little bit weird, that's why we got something a little bit different. But you should get something close as long as you're rounding, reasonably okay. By the way, if you encounter a multiple choice question like this, and the answers are really, really close together, like 84.4, 84.1, something like that, then you should go back and use more decimal places. So don't round as much, and then you should get the right answer. But usually we'll keep the answers spaced out. But if you see that could just be a rounding thing. But yeah, so as you can see, same kind of question that these always are. So good, it sounds like you've got a good handle on these types of questions. So next week we'll keep going with solutions. We'll have lab on Wednesday, and then it'll be spring break. So, all right, that's it. Have a good weekend. And let me know if you have any questions.